Hi, this is Math 7, Unit 7, Lesson 8, looking at triangles with 3 common measurements today. So as we take a look here, what we're going to notice is that we have different triangles that look the same, but they're going to be a little different maybe in terms of the side lengths or the angles or the order those are in. So let's take a look at those things together. So in the first activity it says, let's examine each set of triangles. What do you notice? What's the same about the triangles and what is different? Okay. So we take a look at these here. We see that they all seem to have the same side lengths. We have a 4, 6, and a 9, a 4, 6, 9, 4, 6, 9. So they all have the same side lengths. That's for sure, right? So we can notice that. So that's the same. It looks as though most of the angles are the same. Like that angle there seems to be very similar to this angle right here, and this angle here, and this one here, and here, and here. So for now, I'm just going to make a conjecture that these are the same angles. And what we notice is different is that they are in different, maybe you want to say they're different directions, right? Might be a different thing. They're faced different ways. You know, this one points to the left, points to the right, upside down. It's like you took the same shape and just twisted it around and flipped it over and drew it different ways. Okay, so in many ways these are the same in a lot of ways, but they're also different in how they appear to us in what we might call their orientation. So the order or the way it's kind of turned and twisted around so you can look at it. On this next set of questions here, or triangles, we see that in this case here, we have some similar numbers again, 41, 83, 56. Here's 41, 83, 56. And these are all the same numbers here. So once again, we can see that they have the same angle measurements. That's the same. But when we look at the side lengths are very different. I can write down different. Different side lengths, right? This one's definitely much longer than say this one here, okay? And if you look, the distance between the 83 degree and the 41 degree is that length, right? That's that one. And here's 83 and 41 here. So if you're comparing those two side lengths, if they were the same triangle, they should be exactly the same. On our other one, our side lengths looked approximately the same. So in this case here, because the angles are exactly the same, we'd actually say we're looking at what we would call scaled copies of these triangles, right? So that means that they are not quite the same. So a scaled copy is going to be very similar, but it's not the same. So while they have the same angle measurements, it's just like I'm shrinking it or enlarging it to make different versions of that triangle, but they are not exactly the same there. Okay? Let's take a look at the next thing. In this next section, it says to examine this set of triangles. And here we have a set of triangles. We notice a couple things. All right, so what's the same about the triangles and what's different? We notice that they all have the same what? Same angle measurements inside of them. Okay, so there's definitely some same angles, same angle. They all have that same 30-degree angle somewhere in that shape. It doesn't mean the rest of the angles are the same, because if you take a look at it, let's take a look at this angle right there, for example. That's a pretty obtuse angle, right? Pretty wide going that direction there. And when I look at the other ones, this is the largest angle right here, and that one seems to be a little bit different than the one right there. I'd have to get out my protractor and really measure that to see what's happening there. And you could take a look at that angle measurement and say, well, what would that angle be? And you know, if I was to line that up like that or so, I'm noticing that if I go there to there, I'm talking about 100 and maybe 30 degrees, a little more than 130 degrees, maybe 135 degrees, something like that in that space there. Whereas this angle right there, the other big one, it's right there, I notice it goes to somewhere about here, maybe 115 degrees. So they're not exactly the same there, are they? We know that they each have two the same side lengths, right? That 5 and 7. But in terms of differences, there are different angles present, and we can just kind of notice that with just looking at it with our eyeball, although we didn't measure it there. We can also tell that another cool thing is that they are in a different order. And what we mean by that, in that different order, okay, is that, let's take for example this first one. We have the side length of a 5 followed by the 30-degree angle followed by a 7. Okay, so in this one we have a length of a 5, we have a 30-degree angle, and we have a 7, and they're all like consecutive, right? There's no gap in between. When you look at this one right here, we're going with a 30-degree angle and a 5 and a 7, so a little bit different order there, right? So they're a little different in the order in which these things are going to be. Notice that this one, the 30 degree is between the 7 and the 5. Over here, the 30 degree is not between them, right? Between them, we don't know what's between them. The 30 degrees over there. Over here, the 30 degrees also not between them. It's somewhere over there. And so this is the angle between them. So the order is a little different there. So when you start to talk about then the next question, which is how many different triangles are there, you have to take a look at perhaps that order idea. Okay, and where does that order stay the same? Let's see if we can find any more where you have a 5, 30 degree, and 7. Okay, where the 5 and 7 have a 30 degree angle in between them. We'd say not there, not there. Here's a 5 and a 7 with a 30 degree inside. Okay, so this one right here matches this one right there. Okay, so that's one. That works out pretty well. Let's see if we can find another one. Let's see if we can find a 5 and then an obtuse and a 7 and 30. Kind of in that order. 5, obtuse, 7, 30. So here, 5, obtuse, 7, nope. 5, obtuse, 7, 30. That seems to work. 5, obtuse, 7, 30. Yep. So this one, because of the order, it's going to match this guy right here. Got that one in place. Here we have a 5 and a very acute and a 730. So 5 acute, 730. This one looks like it, very similar. 5 acute, 730. And sure enough, that one's going to work. So that's going to go there, and that's going to go there. Oh, look over here. 5 acute, 730. That's another one. And it looks the same. Which leaves us with one more. Let's see what that pattern is going to be. This one goes 30, 5, and 7. Here we have 30, 5, and 7. So while there are similarities there between those triangles, what we notice is that we end up with 1, 2, 3, 4 different triangles in that mix. Okay, so don't be kind of overzealous there. If you see the same numbers or side lengths or angle measurements, you have to look and see what's that order, because that really doesn't matter to decide if something is going to be the same, if it's the same triangle or a different triangle or not. Let's take a look at another set of triangles. All right, so examine the set of triangles. What's the same about the set and what is different once again? Okay, so just like the last one, except this time what we see is we have 2 angle measurements are the same. Last time we had 2 side lengths. So we have 2 the same angles and 1 same side length once again, right? They all have 40, 80, 40, 80, 40, 80, and they all have a 6 in there. But what's different is going to be the order, once again, is the difference there. Okay. We can also notice that the orientation, again, is different, meaning the way they're spun and shaped, they're twisted there, right? So let's see what we can figure out here. So how many different triangles are there? That's a great question. Well, let's look at the 6. Let's use the 6 as our kind of guide here. In this case here, the 6 is across from an unknown measure. We don't know what that's going to be, right? Let's see if we can find more. This one has a 6 across from the 80. This has a 6 across from what? The unknown measure. 6 across from the 80. 6 across from the 40. 6 across from the unknown. 6 across from the unknown. And 6 across from the 40. So when we take a look at this, what we can tell is that it looks like I'm either going across from the unknown angle, right? So that's my unknown. 6 to 80, 6 to unknown, 6 to unknown, 6 to 80, 6 to 40, 6 to unknown, and 6 to 40. So let's do the 6 to 80. There's that one. 6 to 80. And then that's 40, 40. So we're going to skip those. So we're going to go 6 to 40. And then 6 to 40. So taking a look at just that side link there, it would indicate to me that we have 3 different triangles. 1, 2, and 3. All right, so kind of a good way of looking at that there for how that works out. The other way you can kind of talk about this here is you could take a look at your orders. So let's say that I call this first one A, and I'll call this one B, and I call this one C. In this one, the order here seems to be something along the lines of, I got 3 down there. I could go 40, 6, and 80 degrees. So I have 40 degrees, a side length of 6, and 80 degrees, right? When I look at B I can look at and call that one 80, 40, 6. So 80 degrees, 40 degrees, and a 6, okay, for my side length there. And C, I have 40, 80, 6. All right, so that's kind of the idea. So you could show that they're different in that way as well. Okay, let's take a look at your summary real quick. It says both these quadrilaterals have a right angle and side lengths of 4 and 5. So they have a right angle and a 4 and a 5. A right angle and a 4 and a 5. However, in one case the right angle is between the two, and the other it is not, and that makes a difference. When you take a look at these things, it matters, the difference matters. And so we can do the same thing with triangles, right? They have a 32, 32, here's a 6 and 5, 6 and 5, but because they're not in the same order next to each other, these are not going to be similar triangles or the same triangle. So keep in mind that that order is very important. You might see the same numbers from time to time, but that doesn't mean that they are exactly the same. All right, so we're going to pause there, let you work on your homework, and then we'll come back and check it together. Homework time, here we go. Are these two triangles identical? Explain how you know. All right, well, we see that they have the same measurements at least. So 70, 70, 95, 95, and 12. A couple things we notice though. We can see that they both have a 70 and 95 next to each other. So that's the same there in terms of the angle measurements, no problem. But that where the 12 is located is what we have to take a look at. Notice that in this case, across from the 70-degree angle is the side length of 12. Over here, it's across from the 95-degree angle. So because those are across from different angle measurements, it tells us the side lengths are going to be different, right? So this is the kind of the long skinny length. This almost looks like a 90-degree angle, for example, 95 about. So the one across from 95 and this one is the long one, and this one's shorter. So they have the same measurements in degrees, but it's a different order. So we would say that they are not identical, and that's because the things are in a different order. Okay, so I like to look at the angle and draw an arrow across to take a look at that. You'll get that later on when you take geometry or math 2 as well, but here it is in math 7. All right, are these triangles identical? Explain your reasoning. Okay, so sometimes it helps if you kind of cover them up a little bit so you can kind of see. This first triangle I have a 70, 70, and a 40, right? So that's what I have there as my first triangle. And I can maybe redraw that real quick. So here's my 40, 70, and 70. And this one here, I have a 70, 70, and 40. So those are my two triangles. Now in terms of being identical would mean that they are exactly the same, right? And you can even tell in our first sketch here, these are not identical. They're not identical, and the reason is they have different side lengths. Right? So between the 70 and 70, for example, on this triangle, it has a length right here of this length. That's the length of that 70 to 70. But when you take a look at the length here of this triangle, 70, 70, it's much, much shorter, isn't it? So those are not identical because they have different side lengths. And that's why we would say not going to work. Same angles, same order, but different side lengths. We'd probably say this is actually more like a scaled copy, right? So it's similar, but not the same. Number 3, Tyler claims that two triangles each have a side length of 11 and a side length of 8 units, and also an angle measuring 100 degrees. But they must be identical. Do you agree? Explain. All right. So what he's saying is that you have a triangle, right? Let's say that it has a length of 11. It has a degree of 100 degrees, and it has another length of 8. And so you make a triangle like that. And that no matter what you do, you'd always make that same triangle. Well, we could probably disagree with Tyler here, and that's because the angles and the side lengths could come in any order, right? I could have an 11 here, and I could have an 8 here, and go this way, and somehow make an angle, the 100-degree angle over here, right? I mean, it depends on how you look at it. This could be the 8, that could be 11, and this could be the 100-degree there. So the order could be different, and because the order could be different, I can make different triangles. So I'm going to say that I disagree, and that's because the order can be different. So you want to explain your reasoning there, and you really want to talk about the order being the thing that makes a difference to make different triangles. All right, number 4. The markings in the number line are equally spaced. Label the other markings on the number line. Okay, we can see here the distance between the two spaces here is a distance of 3. So if I continue here, 0 to 3 would go there, and it continues, and that's a distance of 3. So we're counting by 3s in a positive way, so 0, 3, 6, 9, 12, and 15. And then to go to the negative side, this is negative 3, negative 6, and negative 9. All right. Let's move on to number 5. All right, a passenger on a ship dropped his camera into the ocean. It's descending at a rate of negative 4.2 meters per second. How long until it hits the bottom of the ocean, which is that far away? Okay, so here's the ship, right? And there's a guy up here, and he drops his camera, and it goes down the ocean, and it's going to sink down here and go all the way down to negative 1,875 feet below the surface, and it's dropping at a rate of negative 4.2 meters per second. All right, so what are we saying here? We want to know that it's going to go down to a total of negative 1,875 feet, and it's doing that at a rate of negative 4.2 meters per second, and wanting to know how long that's going to take for that to actually happen. Because they're both negative numbers, I actually don't have to worry about the negative signs, okay, because they're going to cancel out. So if you don't want to deal with them because they're the same, we can do this. So to solve this, then we want to know how many seconds it takes to fall at that rate to get that far. So we've set up our equation like this. We're going to divide both sides by 4.2, 4.2, and then we're going to solve it. Okay. So here is 4.2 and we have our 1,875. So 1,875 divided by 4.2. We're going to take our decimal, move it over one spot there, which means I take this decimal and move it over one spot there and immediately put it up on top and put a placeholder right there. 42 goes into 1 0 times, goes into 18 0 times, it goes into 187 4 times. 4 times 2 is 8, 4 times 4 is 16. So now we start doing some math. So 17 minus 8 is 9, 7 minus 6 is 1. We bring down the 5, and it's going to go into there probably another 4 times. So we have 168 again, subtracting, and borrow. And then 15 minus 8 is 7, 8 minus 6 is 2. So it doesn't go into 27, we bring down the 0. Does it go into 270? Sure it does, about 6 times. So we have 12, carry the 1, 24, 25. And we're going to subtract again, 6. 10 minus 2 is 8. 6 minus 5 is 1. So we're at 18. And we're going to put another 0 right there and bring that down. And 42 goes into 180. Again, we're going to go with something like about 4, right? We can keep going. It's going to go on for a long time. So if we do 4 again, what do we end up with? We've done before 168, and we know that that's not going to be a 0. I'm at 12, and it carries on. I'm going to stop there. I don't want to keep doing this because it's going to be a long number. We want to know how long it's going to take before it reaches there, and we have a pretty good idea here. We have about 446 seconds is about how long it would take to reach the bottom. That's about how long it would take. If you wanted to find out how many minutes that would be, you could divide that by 60, right? So you could take your paper here. You could take a calculator and you could do 446 divided by 60, and that's going to tell you it's about 7.5 minutes. Cool. Number 6. Apples cost $1.90 a pound. How much do 3 1/4 pounds of apples cost? How much do X pounds cost? And then Claire spends some money. How much does she do? Okay, so it's $1.99 per pound. So what that means is that I take whatever amount of apples I have. Let's do this one first. I can do $1.99 times the pounds of apples will give me my cost. And that's what I do every time. Okay, so going back up here, I can do $1.99, and I can multiply that by 3 1/4 pounds. You can convert that to a decimal, 3.25, because a quarter is 0.25, and then I can multiply. So $1.99 times 3.25, and you multiply that out, and get you 6.4695, which we would round that up to about $6.47. Okay, make sure you show your work for how to do that there. Don't just use a calculator. Now, if Claire spent $5.17 on apples, how many pounds did she buy? So again, we take this equation or expression here, $1.99 times the pounds of apples, and whatever she bought equaled $5.17. So to find out how many pounds of apples she bought, the X, we're going to divide 1.99, divide by 1.99, so that X equals 517 divided by 1.99, which is about 2.59 is what I got there. And so if you wanted to estimate that out, you could say about 2.6 pounds if you want to round to the nearest tenth. Okay, and that's the idea. And finally, our last one, number 7. Diego has a glue stick with a diameter across of 0.7 inches. He sets it down 3.5 inches away from the edge of the table. So he sets it down right here on a table. The table's edge is 3.5 inches away over there. That's the edge. How many rotations, oh, but it rolls on the floor. So how many times did this thing rotate around before it fell off the floor there is the question. So this rotation can be found by finding the circumference, right? The circumference is the distance around that circle. So that distance, if we were to cut it and stretch out like a string, we want to see how many of those we could line up before it runs out of space and falls over the edge. So let's find the circumference of the glue stick first of all. Circumference can be found by using a couple formulas. You might know the 2 pi r, if you remember that formula, or circumference is the same as pi times the diameter. They're the same thing because 2 radius is equal to the diameter. In this case, they gave us a diameter of 0.7, so let's use this one. We're going to say our circumference is equal to pi, and in our case here, pi, we can approximate that as 3.14, and our diameter is 0.7. So 3.14 times 0.7 is going to be equal to 2.198. That's our circumference. So we can lay that out there, and in one length is going to be 2.198, right? Now, if I did that again, if I did a 2.198, I know that's going to fit in the 3.5. But what if I did another one? If I did another 2.198, I get 18, 19, carry the 1, 3, I'm at 4. 4.3, I only have 3.5 inches. I'm going to fall off, so I'm not going to make 2 rotations. I can definitely make 1. I cannot make 2 rotations before running out of space. If you want to find out how much rotations you can make exactly, you would take your distance, the 3.5, and divide that by the circumference, 2.198. In doing that, I got 1.59, so it tells me I can make about 1.5 rotations, a little more than 1.5 rotations before it falls off the edge. Alright, that's it for today. Hope you have a great day, and we'll see you next time.